So the next, we're talking about index maps, which basically today we talk this the most. You know, when Chalk was talking about distributed, physics-based, and conceptual, all those modeling, there is some way you have to extract the parametric value, right? And that's what this is about, how you can extract the parametric value, and we'll go from there. The main inputs in a hydrological model, one is forcings, another, you have to define the initial conditions, the third is parametric value. But it's not just like a point laboratory scale we are talking about, is hydrology is a big scale, right? So either you can define that, the big scale, by lumping or in a distributed fashion. The model we are doing here is the distributed one. So we divide all the inputs into grids. I think there are some discussion also presented on what is the size of the grids and all those things. And also this morning when the candidates, participants here introduced themselves, some talked about they know the hydrological, other hydrological models, so the background from other hydrological models. But some parameters are kind of like, it's just for the sake of calibration, you calibrate it, right? And it necessarily doesn't have that boundaries, the limit, values of lower value and upper value through which you calibrate. It can go far and wide in its values. And then you take that parametric values to other watershed. It doesn't represent, even the watersheds are similar. Having said that, the distributed hydrological model is something that you relate the parameter with something that you can measure. And if that's the case, there are a whole lot of satellite data all over around the world. Right? So because of this availability of the satellite data, the main inputs as parametric value that you refer are the soil and land use, and it's globally available. That means a physics-based hydrological model is no more that complicated like we used to think some time ago. And with the time, all this information are getting into more distributed fashion, means that in finer scales. So that's the benefit of getting into the physics-based distributed hydrological model, right? So let's get into some of those index map extraction slides. Basically, the GIS part of explanation lot is done by Chris, and that's how it is performed in WMS. So how it is performed in WMS is that it understands the shape file. The shape file is features, right? So all these polygons, shape file, you import in WMS and you develop a coverage. The coverage is the data with some aspect, for example, soil or land use. Then the WMS helps translate that coverage with some particular numerical integer values for each grid. So this each numerical integer values for each grid, the unique value, is called index value. But then we have to know what that values are. For example, if it is 1 or 2 or 3, 1 could represent sand, right? 2 could represent clay as such. And in terms of land use, for example, if you have used NLCD, National Land Cover Data Set, that has specific default values. And if you can just plug out that values and put into hydrological model GSHA, it understands that, but you have to know what that means. So it doesn't itself understand if it is 11, it's water. It doesn't do that. So you have to have that. The user has to have that knowledge that 11 is water, or for example, 42 is residential, right? So these are some of the things that needs to be understood, what the mathematics within the model and our understanding of that part. So one of these layer that needs to be defined in GSSHA, like Aaron was talking about the drainage network. These are defined by features. Within that, you put a lot of parameters. Some are the roughness parameter itself, right? How smooth is the channel? The next could be soil. Now, having said that, soil is available all over the world. Not single source of soil is available all over the world. Some are more fine, more detailed that we use here in the US, so-called sorghum, right? It's 30-meter resolution. But if you go worldwide, there could be some particular data set that could be at finer resolution. But in general, the one that's whole world available is pretty coarse resolution, 1 kilometer. But even that is not too bad when you take like big scale watershed modeling, right? So that's called FL soil type. But the difference between these two sources is that soil is not directly attributed or directly linked to the so-called features. Then you have to link that, the soil type, the texture, basically, to that features. So there comes the linkage of these feature and the table that defines finally some kind of index values, right? So as like I mentioned before, another important is land use. But where these soil and land use is important role in physics-based parametric data set, we'll come to that point. I think Chalk is talking about infiltration, the next lecture. So in infiltration, in GSSHA, we have recharge equation, the most defined one to interact with the surface and subsurface. Likewise, there are simpler, Green and Am. All these models, the most important dominating parameter in soil, there are all soil characteristics that define the soil characteristics. The most dominant is hydraulic conductivity, right? So, and that hydraulic conductivity depends upon the soil texture. And we take that information from the literature, where in the literature, like Brooks and Kearney or Rouse, who has done intense laboratory, in the laboratory said some kind of relation between the texture and the conductivity. So that kind of information is physics-based, which we take account in this physics-based distributed hydrological model. Likewise, in routing, we talk about all these schemes and how it routes and how the answer for the hydrograph translation of the wave, right? And the most important parameter in hydrological routing is the Manning's roughness. So that roughness is well defined with the land use type or land cover. Different vegetations has produced different kind of roughness. So how it obstructs that flow has been well studied. And that's also physics-based relation we extract into the hydrological model here. Another issue comes is now every model, the physics-based and lumping is a different topic. If you take a big coarse resolution grid, then you are lumping everything in a coarse resolution grid, right? But if you take like really fine, then you have the more details of that. So having said that, it depends upon how coarse resolution you are taking as a grid. Unlike other lumped equation, application is defined in other modeling schemes. Like Chris mentioned this morning about the, what do you call, the hydrological groups, in that he talked about the soil types, and all these defines how much effective runoff would be produced. So that is used in some other modeling schemes like conceptual, like card numbers, right? But any model, ultimately, we are going to turn up the knobs that we call degree of freedom, and we try to match that so-called, and this specific process is called calibration. But after the calibration, then we think that is valid for that event or in the long term. But some other special parameters and things that keeps on changing with the wetness condition and things like that. And then at that particular instant, it's not following the physics process. So the uncertainty lies in that case. So there is a big thing about how we can reduce the uncertainty. And relating to the physics-based hydrological model, I think that's the best platform how you can explicitly reduce the uncertainty. So soil data is directly related to infiltration, like I talked a little while ago, and Chuck will define that in details about infiltration process. One of the parameters is hydraulic conductivity. So different states has different way how it defines that relational database. For example, Sorgo, it has that texture classification done. But for example, FA or soil type, if you look into that, it only has that unique values for different soil types. But then it refers not sandy clay or clay loam or something like that. In another Excel sheet, it provides the percent of sand, silt, and clay. So having that information of sand, silt, and clay, unlike sorghum in FAO type, we have to get back to getting into the textural triangle. The textural triangle then defines or gives us the information. What is the soil type, or what's the texture of that particular soil? So there are different ways or different sources to extract that soil information as what type of texture.
Yeah, lately, my experience has been the last couple of models I've done. StatsGo is the coarser one. That's the one at 250,000. Surgo is the finer one.
Yeah.
Generally, StatsGo is too coarse and Surgo is too detailed for watershed models.
Right.
So you got to kind of combine the two of those together in some.
Yeah.
That's what we did in San Am. Because,
Yeah.
Down to the, because Surgo is a soil database done for agriculture. So how do you plant plants on a hillside? Or what kind of, so it's very detailed, which is a lot more detailed than you need in a hydrology model. But StatsGo is too coarse. So it's just the last couple of ones that we've done, it seems we've made our own kind of combining both of them together.
Anyways, we have to combine, because not all places, if you look into Sorgo data, not all places has that texture values. So there are voids or null values in a lot of places, even in continental US, right? We are talking about that. So we have to mix another source in that areas where there is no data available for Sorgo. I think Chris, do you know how the places where there is no Sorgo data, how WMS puts that under the source, or how it defines the values of soil texture where there is no sorghum soil texture values.
Here, pick one.
It's like nearest neighborhood kind of.
There's no data,
Yeah.
I'm not sure what it does.
It asks you what you want to do. I
So,
think there's spots in
Yeah.
the tutorial where
Right.
they ask you and you say, make it type 25 or whatever.
right. So, yeah, one of the answer could be like, you define the nearest neighborhood cell to that, right? The next would be, what is the dominant soil type? Then you define that to the values that's void. Or you use another source and then fulfill that part. So still we are there. It's like the features doesn't have the information itself. So you have to join the relational database and pull the information of the soil texture. And I think I touched this topic a little bit earlier, the hydro group. So there are, the index can be different concepts that can bring out the index. For example, in this case, hydro group is meant for particular extraction of information for carbon number. Likewise, we are doing on our own like research and development. For example, how we define permafrost, thermodynamics, right? And it does use a lot of information within that, the GIS information. This could be the soil type, the vegetation, and also the topography, the aspects and the slope of topography. Including all those, it gives the information of the frozen ground information. Through that, what we can find the information also is what would be the thermal conductivity, right? Just like we have the hydraulic conductivity, the thermal conductivity. So that could be used another source of index mapping. So it's not confined to just soil and land use, but it could be a combination of soil, land use, and also the topography, right? So this is basically from the National Land Cover Dataset, but also in land use, there are other sources like AVHRR, which is 1 kilometer. Just like I talked about FAO, that's 1 kilometer for the soil. AVHRR is another source for land use, which is 1 kilometer. But here, this is NLC, the National Land Cover Dataset, which is 30-meter resolution. And all these forest, bare land, industrial has particular number that is defining its grid cells, and that is the index. So here in GESA, if you go, if you are working in a GESA project today, I don't know if you went that far or not. There is, when you go to 2D grid and you have produced that coverage, in 2D grid, then there is an option called tables. In that table, then you can define mapping table, right? If you go to mapping table, then there are different processes outlined in that table. For example, one is roughness, another is infiltration, another could be soil erosion. Even soil erosion needs this index map, right? So if you go there, then you got to press which map you are going to use for that particular, defining that particular parameter. Then if you have created 2D grid index map for land use, then you are using that index map to define different roughness through that land use. And how you define the values of soil properties, soil parametric values, or roughness or routing parametric values. These are in GSSHA, a whole lot of those values that came out from a lot of modeling done so far, and also reference to the literature, the pioneer literature. We have that value. So we take out that value as initial parametric values, but that's not final. Then again, ultimately you have to follow up on the calibration to finally tune that. But the goodness of it, if we are satisfied, the best way we are satisfied is how that parametric value can be stable from one event to another. We call it verification, right? Even better verification could be, you have a catchment here, which is, for example, infiltration axis applies, right? So it's arid and semi-arid region, watershed, and we calibrate it there. And if there is similar situation in other catchment, so-called similarity, from the similarity analysis, and we take that parametric values to another one, because we don't have all the places gazed. Not all the places are gazed. Most of the places are ungazed. And ungazed basin, this is a big problem in hydrology. And every time we have to go worldwide, defining what is the hydrology in different places, right? So I think that's the best place where physics-based hydrological plays an important role to reduce uncertainty and define output in terms of physically available environment and soils and land use, which is all, most of those data are digitally available through satellite imagery. So. These are just the land use classifications that's done in NLCD, like 11 is residential, commercial services, but it doesn't have to be 11. When you define in GIS, it could be 1, but you have to know that's 1, so you put the right value for 1. Another thing, finally, we talk most about getting that parametric values from WMS through power arrays. But it can be done directly too. Sometimes if you are just using another source, map source, for example, any features, right, or raster. So if you have a raster, then you can convert that to ASCII. Once you convert that to ASCII, you can clip out all those ASCII values within that watershed so that each grid has a value, the ASCII values. And then you just name an extension index, right, for that particular file. And there is an import option in GSSHA where you can import that index map directly, the ASCII index map directly, and go from there. So having said that, there are options, other options, which could be handy at times, how you define or how you develop the model. So, thank you.